All right. So unit three is on acids, esters, and proteins. Excuse me. I keep doing that. Acids, esters, and lipids. Okay, and acids you're pretty familiar with. There's a vinegar, acetic acid. From 305, you've talked about acids quite a bit. Um, but not in 305. You haven't talked about esters much, if at all. And esters happen when we have an acid and alcohol coming together. All right. So these are the different ways of writing carboxylic acid. Um, Normally we don't write it like this. This is the preferred way, or this way. If we do it in a line drawing, it's going to look something like that. The main thing is the COOH. COOH. Um, there are many common names for carboxylic acid, but there's a lot of IUPAC ones out there as well. It's kind of a mixed bag. Um, this one is probably the most common acid you're familiar with, acetic acid or vinegar or ethanoic acid. Um, all commercial vinegar is 5% acetic acid. And if it's not 5%, what they do is they'll change either dilute it to 5% or and what they call it, enhance it to 5% by adding acetic acid into it. Okay, you all heard of fatty acids, the omega-3s and all this stuff. And fatty acids are just um, long chain. This one I just happen to say is 16 carbons, but they can vary. There's short chain fatty acids, medium chain fatty acids, and long chain fatty acid. And that's just how long the carbon backbone is. And biochemically, they're kind of different. They have different health perspectives. And some of you I know are doing that as a project. Um, I don't know if Gina's online. Um, Gina, you were doing short chain fatty acids, weren't you? Maybe Gina's not online.
She is. She's just chatting because her mic doesn't work.
Oh, all right.
But yeah, she said in chat. Yeah.
She also had laryngitis. Is another reason why she's chatting. Okay. All right. The IUPAC way of naming organic acids is just like before. We identify the longest chain containing the functional group, and that includes the carbon that's got the carbonyl and OH attached to it. And then the second thing is you um, look at the functional group, and for acids, it's going to be oic acid. And then lastly, we look at branches that are not on the uh, carbon backbone. Remember, the carbon backbone has to include the functional group. In this case, it's COOH. And then we have a benzene-based carboxylic acid, which is called benzoic acid. And then the acid group is going to determine carbon number one. Now, the thing that's distinguishing about acids is the acid group is extremely polar, and they frequently will get together when they're in solution and team up together. They're called dimers, where the OH group of one bonds to the carbonyl group of another, because the carbonyl group is got partially positive, partially negative. And of course, the OH group is hydrogen bonding. So the positive on the hydrogen bonding is very strong. And so the symmetry of the acid group is such that they can easily hook up together. Of course, because they're very, very polar, they have very high boiling points. Now, in carbon in units 1 and 2, we have found that alcohols have the highest boiling points. Well, now we have one that's even higher, and that's carboxylic acids. So if we look at a similar molar mass or molecular weight, notice the boiling point goes from low, which is an alkane, to the highest, which is the acid.
Stop the flow along Mediterranean aid into the strip, but it resumed.
I didn't catch that. Say again. Were you asking a question or just commenting? Okay. And here's our good old graph that we always say. Okay, notice again, carboxylic acids at the very top. Okay, because carboxylic acids are extremely polar and water is very polar, carboxylic acids can be very water insoluble, except for we start getting long nonpolar backbones. And the LDFs in the polar and that should be LDFs in the nonpolar backbones add up to such that they can overcome the extremely polar acidic end. And again, carbon 7 is always the key. So carbon 7 and above are insoluble, even though the acid group is very, very polar. Okay, so I'm going to talk about what is an acid here. Okay. The definition of an acid, there are like 6 definitions. The most common one is they disassociate. A hydrogen ion. If that happens, it's an acid. However, there are strong, weak, and non-acids. A strong acid disassociates 100% of a one or more hydrogen ion. Example, that would be sulfuric acid. there are 7 strong acids in the world. 2 most common for us in this class is hydrochloric acid, HCl, and sulfuric. And we use these routinely in organic lab. The other ones, nitric acid is fairly common in a more advanced organic lab. And most of the other strong ones are not used much at all, unless you get into industry or high-end academic labs. Okay, if it's not a strong acid, it could be a weak acid. A weak acid still disassociates but it's not all of them. Only part of the H's become disassociated. Acetic acid is a very common one. Okay, so that H here. Now, the deal is if a compound has an H in it, it could be an acid. But unless the H disassociates as H plus, it's not an acid. So we can have, for example, ethanol. Ethanol has got lots of H's, but none of them disassociate. Now, whenever we have an acid, when it disassociates, what's left over is called the conjugate base. And let me emphasize with weak acids, there is more of the original acid than the conjugate base. With strong acid, it's 100%. And just because it has an H doesn't mean it's an acid. Ethanol, the only alcohol that's a weak acid would be phenol. And that's because the benzene acts to stabilize the conjugate base. Now, how strong an acid is directly proportional to the stability of the conjugate base. The conjugate base is very stable, then it's a stronger acid. If the conjugate base isn't particularly stable, you have a really super weak acid. Okay, does that make sense?
Yeah, I think so far.
Okay. So a acid in plain water will dissociate, mainly because the water is highly polar and it will tend to pull off that hydrogen. So this is something that I'm going to be harping on in Unit 3 and Unit 4 is under different acidic conditions, what is the ionic character of the acid or base? Now, the opposite of an acid is a base. It disassociates an hydroxyl ion as opposed to a hydrogen ion. Okay, so let's look at this in more detail. So, so low pH. Low pH is acidic conditions. High pH is basic conditions. And in between is pH of 7. So with acids, even at pH 7, will generate the dissociation of a hydrogen ion. So if we can have like acetic acid under pH greater than 7, that means it's basic. It's going to pull off the H. So we're going to end up with and that H is going to combine with water, excuse me, combine with hydroxyl ion, and this is going to become water. Okay, acetic acid in pH less than 7, there's no visible reaction. Now we're going to find with bases in pH greater than 7, nothing happens. In pH less than 7 means we're going to have a reaction. So this is going to mean oops, I got that opposite. Okay, pH less than 7, there's nothing to pull off that hydrogen. And pH greater than 7 in an alkaline or basic environment, what happens is this hydrogen reacts with the OH and becomes water. Okay? Make sure you know that.
Can you repeat that, please?
Okay, so an acid, regardless whether it's strong or weak, this is most important with weak acids because it depends on the stability of the conjugate base. But basically, in a alkaline environment, pH is greater than 7. What happens is the OH in the alkaline or basic environment pulls off the H here. Not the H's over here. Remember, there are 3 H's over here on the end. Those are super stable and those stay put. It's the H here on the end of that oxygen that comes off. And what happens, it comes off and forms water. And this is the conjugate base. In a acidic environment, there's nothing to pull off the H. So what happens, the acid remains intact. Let me redraw that. Oops. Okay,
Yeah, thank you.
like we're going to find when we get into unit 4 on proteins that amino acids have both an alkaline end and a acidic end. So what happens is the acidic end feeds the alkaline end, and it forms something called a Zwitter ion. It's kind of a cool concept. Okay, and that's basically what they're talking about here. This is the conjugate base. Okay, so here we have a basic environment. So this is going to be a pH greater than 7. And then we have the OH of the sodium hydroxide combining with the hydrogen of the acid, forming water, and the corresponding salt, the leftover sodium. So I was just reading an article today on MSG. MSG is monosodium glutamate. So there's an amino acid called glutamic acid. In a physiological pH environment, the pH is 7.4, so it's ever so slightly alkaline. So the glutamic acid then is no longer glutamic acid, it's the acid salt. So monosodium glutamate is the acid salt of glutamic acid, and which is a naturally occurring amino acid. And it's not bad for you except for people that are sensitive to sodium or allergic to it. Very few people are allergic to it. It's in 1968, I believe, a Japanese scientist isolated the umami flavor component, and one of them is glutamic acid or the sodium salt of glutamic acid. But there are some non-scientific studies done that associated a certain discomfort with MSG, but they were scientifically horrendously poorly done. And there's no real connection between monosodium glutamate and health effects, other than excess sodium. Okay, here's benzoic acid. Here's the sodium salt of the acid. Also the conjugate base. Okay, so to name a acid salt, okay, you start with the name of the acid from which it comes. So the acid from which this comes from is benzoic acid. And what you do is you take the oic acid of the name and replace it with O8 for the acid salt. So in this case, it's the cation is sodium. So we've got sodium benzoate. Now we're gonna run into two eights in here. One is from the acid salt, the other's from naming an naming an ester. Okay, a lot of the physical properties of acids, organic acids, is carbon length of the backbone. Long carbon lengths means it's insoluble. It's going to be more and more insoluble in water, starting at C7. Now you're going to be having to know some acids in this course or in this unit. So palmitic is one of them, oleic, linoleic are all ones you're going to have to know. Okay, so once you identify the backbone, you look at how many carbons are in the backbone. And usually organic acids are not branched. They are, a couple are branched, but most of them are not branched. And they also come in even numbers. And the reason why they're in even number is how your body generates fatty acids. It's in units of 2. That's why you always see even numbered fatty acids. Okay, acid salts are very common. And to make a buffer, a pH buffer, you need 2 items. You need the acid plus the salt together. So for example, sodium citrate and citric acid together make a buffer. So to determine the pH of your buffer, what you do is you go through and look at the equilibrium constants of all the weak acids. And you choose one that's appropriate for the pH you want to buffer the solution to. Citric acid is frequently used as a buffer. Citric acid, excuse me, is a triprotic acid, meaning there are 3 hydrogens that can come off. And you would mix that with citrate. And based on how strong the weak acid is, it'll determine the buffering capacity of that. Now, did you cover buffers in 305?
I don't know about everyone else, but it was a while ago for me, so I don't really remember. Maybe if we go over it a little bit, it might jog. I don't know.
Okay. Okay, there's all kinds of buffers in life. The acidic buffer is a combination of, like I was saying a few minutes ago, an acid plus its salt. So what happens is if you have a buffer, and what happens if you throw in, and it's set at a certain pH, could be pH 8 or something like that. If you throw in an acid, what happens is it absorbs it and maintains that pH. If you throw a base in, it absorbs the OH and maintains the pH. So if you're looking at a buffer of pH 8, you can throw in, now this is to a degree. If you throw in a whole bunch of acid or a whole bunch of base, then this doesn't work. But in fact, let me talk about the way our body buffers pH. Okay, so Okay, so this is baking soda. And this is carbonic acid. Basically, that's CO2 and water. Okay, on your body, we have this guy attached to a protein. So if we have an H come in, what happens is the H goes there and it becomes carbonic acid. If we have an OH come in, it reacts with the acid over here and forms water. Actually, let me okay, so in your body to maintain 704 pH, and except for your stomach, most of your body is 704, unless you're got something to mess that up with. So if we all of a sudden have an acidic environment, like we breathe too much, like we hyperventilate. We hyperventilate and introduce lots of carbon dioxide, which produces carbonic acid, which introduces H plus. So what happens then is the H plus and the HCO3 form carbonic acid. If we have a problem where we don't have enough acidity in our blood, that means we have too much OH. What happens is the H is neutralized by the carbonic acid. So both are present and go back and forth depending on what the conditions are. All buffers work like this. Somehow it's got to neutralize any H plus coming in, or it's got to neutralize any OH negative coming in. Now our body is very sensitive to changes in pH. Does anyone know why? Our body goes to great lengths to stabilize our pH. Great lengths. Like, why is pH regulation important? Okay, our enzymes have something called an active site. That's where all the magic happens with an enzyme, is not the active site. Enzymes are proteins. Proteins shapes are very sensitive to pH levels. If you change the pH, the shape of the protein changes. The shape of the active site changes. Hence, the active site is no longer active, so the enzyme is useless. Our body has to have working enzymes. Otherwise, we don't live very long. So if we have goofy pH in our bodies basically can't function. So our bodies have all these mechanisms to make sure our pH remains at a steady 704. Now, there's an enzyme in our stomach called protease. That protease requires low pH to work. It works best at pH 2, which is very acidic. So if you go and take antacids, which is going to affect the pH of your stomach, then your protease aren't going to work as well. So anyway, that's a brief introduction to buffers. And in certain chemistry classes like 400, 401, there's a lot of calculations you have to do to figure out what the buffer contents are versus the buffering pH of that combination. But anyway, that's why baking soda, that's why buffering the pH in your body is so important is because of enzymes are extremely sensitive to pH. They're also sensitive to temperature. So your body also has mechanisms to maintain a certain temperature because of enzymes again. Enzymes change form, called conformation, with temperature changes and pH changes. Very, very important. Does that make sense?
Yeah, totally. Enzymes don't work, we don't work.
Exactly. That's right. It's real simple. Now, esters. Esters form when we have an alcohol and an acid. So now it's just like when we had acetals and ketals, we have secondary and primary backbones. So the primary backbone is going to be coming from the acid, which is going to be in yellow. The secondary backbone comes from the alcohol. Just like when we did aldehyde, ketone, excuse me, alcohol. So now we're going to have okay, so this alcohol now is going to attach. So we're going to end up with primary, secondary. Now it stops there, does not go any further. So it's analogous to the last chapter's aldehydes, ketones interacting with an alcohol. We just get a slightly different endpoint because we started with an acid rather than an aldehyde or a ketone. And that combination is called an ester. So you need a name for that combination. So an acid has got an H here. An ester's got an alcohol there. Esters are a big deal in biochemistry. Fats are made up of esters. When we made soap, we had something called a triglyceride, which is a series of esters. Long fatty acids attached together via an ester is called a triglyceride or fat or oil. Esters are found all over the place in biochemical molecules. Some of them are fragrant, some of them aren't as fragrant. They're used as flavoring and fragrance units. They're just all over the place. Okay, there are three ways to make an ester. Three ways to make an ester. One way is with the acid. Let's see, this is number one way to make it. So we have an acid and an alcohol. Now it could be a phenol, which remember looks like this. And we need to throw in a little bit of acidic conditions and heat, and we'll end up with a ester. Now, in my other school, we had an ester lab, which was really fun. Students loved it. We took butyric acid, which is very smelly. Butyric acid is what gives cow dung its smell, is butyric acid. Very awful. And we throw in some ethanol. And what happens is we get this strawberry flavoring and strawberry fragrance. It's amazing how things change. Amazing. It's and so it's funny, the waste container for this lab smells wonderful because all we're doing is making all these esters and stuff that smell great. And down here we make wintergreen, oil of wintergreen. So it's pretty cool. Okay, let's look at this now. We haven't talked about naming yet, but remember, esters come from an alcohol and an acid. So the name is going to incorporate the alcohol and the acid. So this came from an ethyl alcohol and a butanoic acid. So this came from a 2-carbon alcohol, and that came from a 4-carbon acid. One carbon alcohol. Oh, this is complicated. It's got 7-carbon salicylic acid. Okay, so that's method number one. Acid plus alcohol gives us acid plus alcohol gives us the ester. Now, when we start naming esters, we have to include the alcohol part and the acid part. Alcohol part is named first, and it's named as a branch, ethyl. And on the acid part, we're going to substitute oic for O8 on the acid. Okay. Method number two is going to involve the acid chloride plus the alcohol. Method number three is the anhydride plus the alcohol. 3 ways. The acid chloride gives the most yield, and the alcohol acid gives the least yield. three ways. And you're going to need to know these three. Because I'm going to ask you, a typical test question is going to be, how do you make this three different ways? So for example, okay, so this is an ester. And we know it's an ester because we have this here. So that means it comes from two parts, an acid and an alcohol. So the acid has got 1, 2, 3 carbons, and the acid has 2 carbons. So to make this, we're going to combine a 3-carbon acid plus a 2-carbon alcohol. And that'll give us this here. Okay, that's method number 1. And method number 2 is the alcohols all are the same. What changes is the acid derivative. Okay, so we still need a 3-carbon atom, 3-carbon acid, but this is going to be from the acid chloride. Let's see, I need more room here. Let me. Okay, so the acid chloride, there's no OH, there's a Cl there instead. Okay, so we use the acid chloride, we're going to end up with HCl and the ester. And then the third way is when we use something called using an anhydride, which is the most common way. An anhydride are two acids coming together to form two esters at the same time. So let me give you an example of an anhydride. Okay, so that's an anhydride. So if you cover, what's the best way to do this? Let's see. I'm going to redo this in different colors here. So here is ester 1, and here is ester 2. Now the acid part here, in the case I just did, is the same ester. It's a 3-carbon ester. Doesn't have to be though, it can be different lengths. Normally, when we're doing simple esters, we use the common anhydride, and this is an anhydride. Let me check one thing here. I always forget whether there's 2 ends or 1 end. And there's 1 end. I always want to put 2 ends in here. I don't know why, but I just do. Okay, so an anhydride is 2 esters and a common oxygen from the alcohol. Okay, so when we make aspirin next week, we're going to use the anhydride. So now let's make this ester here. So whenever we make the anhydride, we always end up with hydrogen, excuse me, whenever we use the acid chloride, we always end up with an acid, in this case, hydrogen chloride or hydrochloric acid. When we use the anhydride, we're going to end up with the whole acid coming from the anhydride because the anhydride, remember, is 2 esters together. So one of the esters goes to the acid, the other ester continues on with transesterification of the new alcohol. Okay, so what we need is a 3-carbon acid. So that means each side of the anhydride is going to be 3 carbons long. Three carbons. And we have, let's do this in my original colors. Okay, so now we have the anhydride. So here's the acid part. which is going to correspond to now this part here, let me do some below, is going to become an acid. No, it's 3 carbonyl. This is 2 carbon. Okay, 3 ways to make an ester. Okay, so this is the most yield again, least yield, middle yield. Okay, you might ask your question, why wouldn't you always use the one with the most yield with the acid chloride? It's because the shelf life of acid chloride, because it's very unstable, that's why you get a good yield, is very short. So they're very expensive chemicals to buy. Using the acid the acid part is stable, but you don't get very good yield. So what you use is the middle one, the anhydride. That gives us the most shelf life, not the best. The acid gives the best shelf life, but the anhydride is a nice compromise between good reactivity and shelf life. Okay, so those are the 3 ways we make an ester. All right, and you need to practice this a lot. Practice this a lot. So here we have a 2-carbon acid chloride. Here we have a 2-carbon alcohol. So our ester is going to be a 2-carbon on the acid side and a 2-carbon on the alcohol side. So we haven't got into naming yet. We're going to get into naming in a second. So here we have phenyl acetate. Okay, here's the alcohol part. Here's the acid part. 2-carbon. Excuse me, 6-carbon. All right. So the primary backbone comes from the acidic part of the ester. That's the acidic part attached to the carbonyl group, the double bond. And the secondary backbone comes from the alcohol part. So acid, alcohol. So the my winter cough is returning, excuse me. Okay, so to name this with the quote unquote IUPAC name, even though this is an accepted common name is IUPAC, I want us to use the IUPAC name, the original one. So we're talking about this is the alcohol part, one carbon alcohol, one carbon alcohol. So that's a methyl, two carbon acid. So that's an etha, like ethanoic acid. This is going to be ethanoate. So this is okay. So this is the ester salt. Um, we have alcohol, excuse me, we have acid salts and ester salts. Ester salts come from an ester. Alcohol salts come from a deprotonated acid. So let me write that over here. To get an ester salt, you need to have just another name for ester. Okay, let's look at this one here. Okay, we've got this ester's got four carbons and it's got a benzene ring here or a phenyl group. Okay, so that means it's going to be phenyl butanoate. So four carbons, O8. Now remember, the other way to do an O8 is with the acid salt. So sodium, I mean, let's bring it over here for a second here. So we have sodium. Okay, so whenever we see the O8, with O8, that could be an ester or a salt. How do you tell the difference? Okay, an ester is going to have an alcohol in front, and a salt is going to have a cation in front. Usually sodium or potassium. So sodium bentoate, sodium automatically means this is salts. Ethyl is an alcohol, so that means that's an ester. So this next one here, C part C. Okay, we've got a two carbon alcohol and a aromatic acid. So this is going to come from benzoic acid. This would come from ethanol. So to name it, we go alcohol first, so that's ethyl. Next comes from the acid, okay? So it's going to be, instead of benzoic acid, we're going to say benzoate. So it's ethyl benzoate. And lastly, esters can come and go. So esters can be taken apart as easily as they're put together. So for example, when we take apart an ester, because it was created with an alcohol and an acid, we end up with an alcohol and an acid. Okay, so ethyl propionate, ethyl meaning it comes from a ethyl alcohol, 2-carbon ethyl alcohol. And we're looking at 1, 2, 3 carbon acid. So that's propanoic acid. Now, if we're this is an acidic environment, pH less than 7. If we're in a alkaline environment, we don't get quite the same thing. We get the alcohol, but we get the sodium or potassium salt of the acid from which you started. Okay, we started with 3-carbon 3-carbon acid on the left. So we're going to end up with a 3-carbon acid in an acidic environment. In a basic environment, we're going to end up with the salt of the acid. So this is the acid, and here's the salt. And when it's in a basic environment, it's called saponification. Now, typical test question is, I'll ask you, can you saponify this chemical? So you look for one. Okay. So you look for an ester. Is there an ester here? There's an ester right here. Ester present, yes or no? Number 2, what's the pH? If the pH is greater than 7, it's a yes. If the pH is less than 7, it's a no. So that's why when we make soap, we want the acid salt of the soap. That means we need to have a basic or an alkaline environment to take those esters apart on the triglyceride. I'll go into that more in detail on Wednesday. Okay, so we're going to end up with some examples here. Okay. All right, so we have ethyl acetate. Acetate is 2 carbons. Ethyl alcohol is 2 carbons. So we have ethyl acetate in a pH is less than 7. Acidic environment. That means we get this acid plus the alcohol. So let's do the same reaction in pH greater than 7. So we have ethyl acetate. Okay, so we have 2 carbons, and we have let's see how to do this. Okay, so we have a pH of 7. So what we're going to do is make it bigger. So this is the acid side, alcohol side. So with pH greater than 7, we're going to end up with the salt. So let's say this is potassium hydroxide. Let's put those in 2. Okay, so we're going to let me do it slightly different. Okay, so we have the alcohol and we have the acid. Okay, the acid is not going to be an acid. It's going to be the acid salt. This is going to be 2 carbons, going to be potassium ethanoate. And 2 carbon alcohol. This is going to be ethanol. So so and so this um, ethyl ethanoate is going to be saponified because it's in a basic environment. It's going to be saponified to the acid salt plus the alcohol. In this case, it's going to be potassium ethanoate and ethanol. Okay, and this requires practice. Okay. This is what I just did. Okay, so that's what I wanted to cover today on alcohols and esters in various pH environments. So, oh, by the way, I'm going to modify the class schedule. And instead of 5 units, we're going to have 4 units. And instead of 5 tests, we're going to have 4 tests. Because I want to give more time to each unit, because I find I'm rushing the units. I'd rather have you learn them better and cover less material. Okay, so any questions about these guys? And you've only seen this for the first time, so you need to practice it. But anyway, go ahead.
Yeah, about the something being saponifiable,
Yeah.
just like the overview of the steps. It was like look for an ester, have the pH over 7. I forgot the rest. I didn't write it down. I was just listening.
Okay. So, is there an ester present? That's yes or no. And what's the pH? If the pH is greater than 7, it's a yes. The pH is less than 7, it's no. The ester still comes apart, but it's not considered saponifiable. The products are different also. In the case of saponifiable, you end up with the acid salt plus alcohol. In the case of an acidic environment, you end up with the acid plus the alcohol. Is that better?
Yeah. Thank you very much.
Let's see if canvas is working.
It is still down currently. They have the East Coast. Sorry, they have the East Coast working, kind of, and they're like trying to roll it out to the rest of the country.
All right, well, anyway, I'm going to revise the we just have to, I'm just looking at the chats real quick here. Okay. We have to once Canvas comes up, look at the new schedule. The labs are going to remain the same, but the lecture topics are going to be a little different. So the labs coming up, we've got one dry lab on sunscreen, and we've got an acid, not an acid, a aspirin lab that's in 2 weeks. Next week is we synthesize aspirin, and then after that we identify exactly. You make your own topic, as long as it's organic or biochem. And then on the second week of the aspirin synthesis, we're going to actually determine the molar mass of the aspirin and compare that to the real molar mass. The closer we are to the real molar mass, the more pure it is. But it's a pretty cool lab. We're going to use some filtering techniques next week using vacuum. So instead of waiting a half an hour for something to vacuum, we're looking at 3 or 4 seconds. It goes really fast because you do a lot of filtering in this lab. So anyway, we're going to use the more advanced organic technique using a something called a Buchner funnel under vacuum. So Kaylee, regarding topic, it's kind of yeah, exactly. Anything you want. It's if you have something, for example, one woman in my Sierra class had a horse accident, and the horse she was out riding, and she the horse fell on her leg, and she ended up being partially crippled from that. So what she did is she did the analysis of why her muscle wasn't responding, which is a calcium issue, calcium transpons issue. And for example, another person did it on, she has a syndrome where she can't digest foods very well. So her supplement are 3 enzymes, one to digest carbs, one to digest fats, one to digest proteins. She did it on that. Another did it on science of dying, very biochemical base. Another person did it on short chain fatty acids, which is, I think Gene is going to do that. Anyway, it's just a biochemical or organic base. Some people did sodium benzoate as a preservative, how it works. Some people did it on how a breathalyzer works when you get a traffic stop, because that's organic chemistry based. Does that help? And you run the topic by me. Okay. All right. Let me know, Kaylee.
Okay, so on this next week, this week then is the dry lab. Next week we have a wet lab, I think is what I saw on the schedule. And I remember when I started, told you I was going on a trip to Japan. I was gonna email you or message you on Canvas, but now that's down. So I thought I'd just mention it, and then once it's back up, I'll send a reminder email so we can figure that out.
When are you leaving?
I'm leaving this upcoming Friday, and then I'll be gone for 2 weeks, and I'll be back on the 10th.
Okay. Um, I'm going to be redoing the test schedule as well because I want to reduce. I think you'll be okay.
Okay.
Either way, we can work it out. So,
Okay.
and next this week is not a dry lab. It's sort of a dry lab because we're not doing a wet lab, but we're just choosing topics. And
Oh,
the when I said wet lab, another dry lab. I'm not counting this week. I'm
I see.
counting because when I envision a dry lab, I envision a worksheet, and there's one on um, um,
Something.
sunscreens.
Yeah.
Okay, well,
Professor, I had one quick question. So I had emailed you last night about the project topic, and asked you if I can do the vanilla ice cream, but you said to send you something over for the chemistry breakdown. But I was wondering instead, can I do my project topic on Taxotere, which is a chemotherapy medication for breast cancer?
yeah, yeah. Just when you do that, show how the medicine works.
Okay, thank you.
Now, if you want to go back to the ice cream, you can look at commercial ice cream. Have you ever made ice cream at home?
No, I haven't, but I was just doing a little research on it. And the reason why that was like my first choice of topic was because just I seen that it had the ketones and the aldehydes in it, but the aldehyde was basically significant ingredient in the vanilla ice cream to aid in the flavor.
Yeah. So you put in vanilla extract, and then or a crushed vanilla bean innards. Um, so if you want to do what's in a vanilla bean, for example, that you eventually goes into ice cream, you can do that. But ice cream itself is just basically fat plus sugar in cold conditions. So there's really not a lot of chemistry there. What's chemistry, if you look at commercial ice cream, things like stabilizers and various flavoring agents, those are all candidates. But just plain old homemade ice cream is it's more
Okay,
physical.
yeah, I think I'll just stick with the Taxotere for the cancer because I'm kind of like more familiar with that topic anyway and can probably do a better chemistry breakdown of it. So I'll just stick with that topic.
Yeah, okay. Okay. No one's done that before, by the way.
Okay, thank you.
Actually, no one's done vanilla either, so. Okay, yeah, as Connor said, there's if you go to um projects on under files, Canvas files, you'll see I don't know about 15 or 20 or 30, I don't know, I forgot how many example posters. And you can see and most of those are from um Chem 306 equivalent, either my class up in Vacaville, up in Tacoma or out of Sierra. So good examples. And then the essay is not a very long essay. 1,000 words is 2.5 pages, depending on how big your font is. So it's not very long. It's just, and think of your poster as kind of the multimedia part of your essay to help visualize it. Yeah, and Shelby, regarding a topic related to your major, that's fine. A lot of times people have someone in their family has a medical issue they like to explore and get credit for it. Sometimes they have their own medical issues they like to explore. Um, I like to do this idea because it gives an opportunity for you to explore something you're interested in and get credit for it. Because in education, frequently that's not the case. Frequently, you're just given a topic and said, write about it. So, okay, so anything else?
Professor,
Yeah,
I know just giving you like our topic is due today, and then once you approve it, that's when we start working on the project. And it's, do
yeah.
you think that the project due date will still be the same? He says December 9th, or is that being changed as well?
No, that'll remain the same.
Okay,
And
thank
you
you.
can turn it in earlier than that also.
Okay,
So you get it done this weekend. Now, if I don't say anything, you're fine. Most people um, like to talk to me a little bit about their topic. The main thing I want to see is biochemistry and organic chemistry with a little general chemistry thrown in, since it's a chemistry class. Um, and chemistry is in basically everything. So usually it's not hard to figure out how you can employ chemistry in your topic. Okay, well, sounds like everyone's got their questions hopefully answered. All right, I'm going to go ahead and sign off and take care, everyone. And Wednesday, we're going to do some more with acids and esters, and then get into lipids. Some real interesting stuff with lipids, besides making soap or ice cream. Some real interesting stuff. For example, if you've heard of prostaglandins, I'm going to talk about how our body makes prostaglandins and why omega-3 fatty acids are important. So it's another reason why you should watch your omega-3 fatty acid input. Okay, everyone, take care.
Take care.